Time feels simple. It feels steady, universal, and fair, a constant rhythm that ticks the same for everyone. But the universe doesn't agree. According to Einstein, time is not fixed at all. It stretches, it bends, it slows down, and it speeds up depending on where you are and how fast you're moving. Your seconds are not identical to mine, and neither of us experiences the universe in exactly the same way. Today, we're going to peel back the illusion of universal time and explore how relativity reshapes our understanding of reality. No equations, no heavy math, just clear ideas, intuitive stories, and the surprising truth that time itself is personal. Time feels simple. It feels steady. It feels like a river that carries everything forward at the same speed, no matter who you are or where you live. A second is a second. A minute is a minute. Your watch ticks at the same pace as mine, and we assume the universe keeps perfect time everywhere. But that's not how the universe works. Not even close. The astonishing truth is that time flows differently for different people. Not as a metaphor, not as a trick of perception, but physically, measurably, provably different. Your time is not my time. Your second is not my second. And once you understand why, your entire view of the universe shifts. Today, we're going to break down relativity in the simplest possible way. We'll explore why moving faster slows your time, why gravity bends time, why GPS satellites experience time differently, why clocks run at different speeds, depending on where they are, and why the universe doesn't treat time as a universal rhythm, but as something flexible and elastic. And by the end, you'll understand something Einstein discovered more than a century ago: time itself is relative. Let's begin with a question that sounds impossible. What if you and I experience time at two different speeds? This isn't philosophy. It isn't subjective perception. It's real physics. Two people standing in different places or moving at different speeds actually age at different rates. One experiences slightly more time than the other. And even though the differences are tiny in everyday life, they're very real, and they become enormous when speeds and gravity grow extreme. So how did Einstein discover this? To understand relativity, we first need to understand that time is not separate from space. In everyday life, we talk about space and time as two different things. Space is where you move. Time is when things happen. But the universe doesn't see it that way. Space and time are woven together into a single four-dimensional fabric called spacetime. Everything you do, whether you walk, sit, sleep, or travel, moves you through spacetime. You move through space by changing position. You move through time by simply existing. And here's the key idea. Your motion through space affects your motion through time. Let's take an example. Imagine the universe enforces a rule: nothing can travel faster than the speed of light. Light's speed, 299,792,458 meters per second, is constant for everything everywhere. It doesn't matter if you chase a beam of light or run away from it. Your measurement of its speed will always be the same. To keep that rule consistent, the universe has to adjust something. And what it adjusts is time. When you move fast through space, the universe slows your time down so that the speed of light remains constant. If time didn't slow down, you could violate the cosmic speed limit. But because time is flexible, no law is broken. This is the beginning of special relativity. The faster you move, the slower your time flows. Let's make this idea simple with a story. Imagine two twins. One stays on Earth. The other travels in a spaceship near the speed of light. For the traveler, the journey might feel like a few years. But when they return, Earth might have aged decades. The twin who stayed on Earth is now older. The twin who traveled is younger. This is the famous twin paradox. And it's not a thought experiment anymore. Versions of this effect have been measured many times. We've put extremely accurate atomic clocks on airplanes flown them around the world, and then compared them to identical clocks on the ground. The airborne clocks ran slightly slower. Not enough for humans to notice, but enough for precise science. The same thing happens on the International Space Station. Astronauts orbiting Earth at high speed age, just a tiny bit slower than people on the ground. Their hearts beat the same. Their daily routines feel the same. But their time is literally moving at a different rate. So speed affects time. That's special relativity. But it gets stranger. Gravity affects time too. This is where general relativity comes in. Einstein realized that gravity isn't really a force pulling things downward. It's the curvature of spacetime caused by mass and energy. Think of spacetime as a giant fabric. When you place something heavy like a planet or a star on the fabric, it sinks in, creating a well. Objects around it follow curved paths because the fabric itself is curved. But this curvature doesn't just affect space, it affects time. The deeper you are in a gravitational well, the slower your time runs. Time literally runs slower near heavy objects. This means that a clock at sea level ticks slightly slower than a clock on top of a mountain. A clock on Earth runs slower than a clock in orbit. A clock near a black hole runs dramatically slower than a clock far away. And we don't have to imagine these effects, we measure them constantly. Consider GPS satellites. They orbit Earth far above its surface, experiencing weaker gravity and moving at high speed. According to general relativity, their time should run faster. According to special relativity, their speed should make their time run slower. Both effects happen, but gravity wins, so overall, their clocks run faster than clocks on Earth by about 38 microseconds per day. That doesn't sound like much. But if engineers didn't correct for this, GPS would be off by kilometers within a single day. Your phone wouldn't know where you are. Navigation systems would collapse. Airplanes would fly off course. The modern world only works because we adjust for relativity. In other words, relativity isn't just a theory, it's part of daily life. Now let's look at one of the most extreme examples of relativity: black holes. Black holes are regions of space where gravity is so strong that not even light can escape. Time near a black hole is radically different. If you were to hover safely near the event horizon, the boundary where escape becomes impossible, your time would slow to a crawl compared to the rest of the universe. You might feel like you're experiencing a few hours. But for someone far away, years could pass. Decades. Even centuries. This isn't fiction. This is real physics. The movie Interstellar famously used this concept. On the planet near the black hole, 1 hour equaled 7 years in the outside universe. And while Hollywood exaggerated slightly for drama, the underlying physics was correct. Extreme gravity stretches time to extreme degrees. The universe is not a place where time is uniform. It's a place where time bends and twists depending on your motion and the mass around you. Let's make this even more intuitive. Imagine space-time drawn as a sheet with 2 axes, one for space, one for time. In everyday life, you move mostly through time, hardly at all through space. But as you move faster through space, your path tilts and you cover less ground in the time direction. Motion through space trades off with motion through time. If you stand still, all your motion is through time, 1 second per second. If you move fast, some of your motion goes into space. Your time slows to compensate. This trade-off is the heart of relativity. Now, let's return to the question we began with. Why don't we notice these effects in everyday life? The answer is simple: because we move too slowly and live on a planet that's not massive enough for relativity to affect us strongly. You walking down the street doesn't change your time in any meaningful way. Driving a car, flying in a plane, none of these speeds are enough to produce noticeable time dilation. And Earth's gravity, while strong enough to keep us grounded, isn't strong enough to dramatically bend time the way a neutron star or black hole does. But when we build extremely precise clocks, we can see the difference. When we launch satellites, we must calculate the difference. When astronauts travel in orbit, we measure the difference. It's subtle, but it's real. At this point, you might wonder, does relativity mean there is no true time in the universe? Exactly. There is no single universal clock. There is no cosmic metronome ticking everywhere at once. Time is local. Time depends on you, your motion, your position, your gravity. Every person on Earth experiences time slightly differently. Every clock ticks at its own pace depending on where it's placed. And every moment in the universe is tied to space-time, not a global timeline. This leads to something profound. Reality looks different for different observers. Your now is not the same as someone else's now. Your passage of time is not identical to anyone else's passage of time. Two observers can measure the same event and disagree on how long it took. And they are both correct. Relativity doesn't just change how we see time, it changes how we see reality itself. Let's take a simple daily life example to bring this home. Suppose you live at the bottom floor of a skyscraper while your friend lives on the top floor. Because gravity decreases with height, your friend experiences slightly weaker gravity and therefore slightly faster time. Over the course of a lifetime, your friend will age a tiny bit more than you. The difference might be less than a microsecond, but it's measurable with the right instruments. This means that even in ordinary life, relativity is quietly shaping everything. So, what does relativity really tell us about the universe? It tells us that time is not a universal rhythm. It's a flexible, stretchy, elastic dimension. It bends with gravity. It slows with speed. It warps with mass. It changes with motion. And everything, planets, stars, galaxies, and even you, moves through space-time in a unique path that defines your experience of time. Einstein didn't just change physics. He changed our concept of reality. Time isn't the same for everyone, and it never has been. The universe doesn't run on a single clock. It runs on billions of clocks, each tied to its own motion and gravity, all ticking at slightly different rates. Relativity shows us that the laws of nature are elegant, subtle, and deeply interconnected. Space and time aren't rigid backgrounds where events unfold. They're dynamic participants in the structure of the universe. So the next time you look at a clock, remember, it's not ticking the same way everywhere. Your seconds are unique to you. Time bends around mass stretches with speed and flows along the curvature of space-time. The universe is not a place of absolutes. It's a place where reality depends on perspective. And that's what relativity really means. Time isn't the same for everyone. Relativity teaches us something extraordinary, that time is not a single synchronized pulse echoing across the universe. It's flexible. It's shaped by gravity-speed motion and the very structure of space-time. Every person, every object, every planet experiences a slightly different flow of time. And yet everything still fits together into a consistent, elegant picture of the cosmos. We don't notice these differences in daily life, but our technology, our satellites, and even the shine of the sun depend on the laws of relativity working perfectly. Time is not what it seems, and understanding that opens the door to a deeper appreciation of our universe. If you enjoyed this breakdown and want more clear story-driven explanations about how reality really works, feel free to subscribe and join us for the next journey. Until then, stay curious, because the universe always has more to show us.